Hello, Stats 300, and this is Professor Gonzalez, and I'd like to do some problems on the assignment side of Alex homework problems 9.2. So now in 9.2, we're getting into hypothesis testing, and some of the tools we're going to need for this in this 9.2. And in 9.2 is one of the differences between 9.2 and 9.3. 9.2 is where, it's only right here, 9.2 is we're looking for statistics for the mean, but 9.2 is where standard deviation is known. And then 9.3 is where standard deviation is unknown, and that requires us to use the sample standard deviation instead of the population, right? Instead of, so this is where what is known? Sigma. And then 9.3 is where standard deviation, this is unknown, right? So we have to use the sample standard deviation. And by the way, this is in front of us right here in the formula. 9.2 is where the population standard deviation is known, right? So we use sigma. 9.3 is where the population standard deviation is unknown, so we use the sample standard deviation, a little less. Okay, so it's kind of laid out for us. Today we're going to be looking at 9.2. So to get our test statistic, we're going to use z equals x bar minus mu sub 0. Now that is our population mean, but it's just the population mean that goes with our null hypothesis. So it's still the same thing as just mu, but it's that mu that it's a population mean that is associated with that 0 or the null hypothesis. So we use the little 0 or null, not, it's called not or 0 subnotation. So don't let that confuse you. But this test statistic that we're finding is just a z-score given z-score from this sample mean from the sample, right? The mean from the sample. Okay, so that's what that is. All right. So, and then another thing that's very useful in 9.2 is that we can use this chart. So I put this chart in here because it is very useful. If we don't have this chart, we've got to go to the z table to figure this out, or we would have to go to, let's say, a calculator to figure it out. But what is this saying anyhow? I think this might be a good thing to kind of show. And I didn't plan to actually do this little part right now. So let's see if I can do it real quick. What this is basically saying for this left-hand test, this left-tailed test, is it's given us. So when we have this significance level, the significance level is actually, significance level, alpha, is actually the area. Now this is a left-tailed test, so we're talking about the left side over here. And they're basically saying that when you have an alpha, let's just go ahead and say 0.10, which would be 10%. When your significance level is 0.10 or 0.1, basically saying, let me use some color, I guess. We're saying that that area is 0.10, that's your alpha. And there is a critical value that you could look up. You definitely can look up. But this chart is nice. Oh, geez, let's see. This chart is nice because it's done for us. If you have a significance level, alpha of 0.10, and what is that critical value that goes with it? Well, there it is right there. That would be z equals, and I wrote down here critical values in the form of z-scores. And it's also when we're looking for hypothesis testing for mu, where sigma, once again, is known. That means 9.2. Anyhow, that value there is just going to be negative 1.282, right? And so that changes, right? If you want significance level of 0.05, then that's moves over a little bit, and it gives you that value for that, okay? Now, what about right-tailed test? A right-tailed test, we'll go ahead and use blue for that. Right-tailed test is very much a similar thing, but it's on the right-hand side. So let's say if we want even a more picky or more, a significant level, which is smaller, which means it's harder, it scrutinizes the data more in some ways. Let's see, so this is going to be my right-tailed test. Oh man, this thing just keeps on popping back and forth. There we go. Okay, we got this right-tailed test. And let's say that right-tailed test is going to be for a significance level that is really quite small. It's a 2% or 0.02. So that is that alpha or significance level of 0.02. And we want to know what z-value is right there associated with that. And we can look it up. Right-tailed test. Let's see, right-tailed test, 0.02. And there's your z-value right there. Okay, and so that's just going to be 2.054. So that's really handy, right? Because otherwise we have to look that up on the z-table or put it in a calculator and know if it's on the right or left-hand side and all that. The one that might be a little bit different in some ways is, let's do this one in green, and that would be the two-tailed. Two-tailed is a little different because it has two tails. And let's do it right here. Let me try that again. So it has two tails, and the thing that's different than with that is that the alpha is actually the sum of these two tails. So let me just make sure that you know that alpha is going to be both tails together, the area of both tails. Okay, so that's kind of important to know. It doesn't really show up on this table as much, but if you're actually going to look this up on a z-table or actually using a calculator to find these critical values, for two tails you'd have to actually take the alpha and divide it in half and split them between the two tails. Okay, so anyhow, that's the difference with two tails. So let's say that we're doing a test, and on this one, let me use my color again. So I want significance level of 0.05. So your alpha there is going to be half of 0.05, right? Because half of it goes there, and half of 0.05, half of it goes there. And then what significance level goes for, what critical values go with the significance level of 0.05? Well, there they are right there. They would be just these guys, this one's a negative 1.96, and this one's a positive 1.96. Okay, so I included this on our notes because it is very handy. And this, once again, is for z values. So this particular chart right here is only going to work for 9.2 in terms of, well, on any kind of hypothesis testing where sigma is known, where you're going to use z scores. All right, let's do some of these problems. So our first problem says a study showed that 2 years ago, the mean time spent per visit to Facebook was 20.2 minutes. Assume the standard deviation is, and when we see this sigma notation, we do know that's population, is 4 minutes. Okay. And it said a study showed 2 years ago. Okay, all right. So suppose that a simple, so you can hear the language change right here. Suppose that a simple random sample. So everything after that, we're talking about sample information. And the information before that, we're talking about population information. So when they said just a mean time spent, well, that would be, I'm going to use mu because we're talking about population. mean is 20.2 minutes. And also they gave us the sigma standard deviation, population standard deviation. Sigma is 4.0 or 4 minutes. And then we get into this sample information. Let's see, the simple random sample was n equals 107. What else do we know? Visits selected this year. So the sample mean, so the mean of the sample is going to be x bar, and that is 19.2. Okay. A social scientist is interested to know whether the mean time of Facebook visits has decreased. Okay, and also note that our significance alpha level is 0.10. Okay, so our null hypothesis is just going to be that the mu, the population mean, is going to be 20.2. Now the challenger, or the question is, social scientists is interested to see if whether the mean time of Facebook visits has decreased. So this is what is assumed and is given. Now the question is, has this decreased? So what is it? Is the population mean actually less than 20.2? Okay, now last time I did some problems, we talked about how to tell if it's a left-tailed, a right-tailed, or if it's two-tailed. And I guess once again, I'll just put that up over here just as information. You always, so let's see. How do you know what tail it is? Tail question. You always look at the alternate hypothesis. If the alternate hypothesis has equality, I'm sorry, I just misspoke. If the alternate hypothesis has a less than symbol, then when you're thinking, when your mind's eye, when you're thinking this distribution, what's less than the mean? What's less than 0? What's to the left over here? So in that case, you're thinking what? Left. And then, once again, when we're trying to figure out the tail, we're not looking at the null, we're looking at the alternate, which is h sub 0. And when that mu, or whatever they're talking about, is greater than, you could kind of, once again, see in your mind's eye, or draw it out, that, remember, the mean is right here, so if it's greater than, our test is going to have to be a right-tailed test to see how far right it is, right? That's what we're kind of testing. We're trying to see how far off the mean is. If it's really far to the right, then we're going to say that, okay, we're going to reject our null hypothesis. We'll get into that. And our third case is when the alternate hypothesis says something like not equal to. And if it's not equal to it, it could be less than or greater than. So we have to test for both sides of it. And that's why it's a two-tailed, because you can't just test above or just below. We have to test both. So that would be two-tailed. Okay, excuse me. So because this is less than, this is a left tail. Left-tailed test. I think I'm about to get a glass of water. Excuse me. So, find the critical values. Values would be because of its two-tail, but this is just a left tail. So, find the critical value, round your answer to 3 decimal places if necessary. There is more than one critical value, separate them with commas. Okay, so when we go look up our critical value, remember we have a chart that's going to help us a lot with this. If we don't have the chart, then we're going to have to use the z-tables, or we're going to have to use our calculator. But so what's really important when we're looking for critical values in this problem? Oh, by the way, this particular problem I want to highlight this, something I didn't highlight. It says, so use a significance level alpha of 0.10, but it wants us to use this critical value method. There's two methods we're going to be using. We'll first do a critical value method, which we're going to do first, and then the second one we'll do our p-value method. Okay, so for our critical value method, to get our critical value, it's super important to know that the alpha is 0.10, and we'll also need to know that it's a left-tailed test. And if you know those two things, and you also know that we have a population standard deviation, that means that we're going to be using the test statistic in a sec. But before that, we need to know this critical value, and we can get this critical value from this nice little table that I kind of showed you earlier. And so let me get rid of some of this stuff so I can use this table a little bit better. I was just trying to explain how the table, or what the table was doing, so it doesn't seem like crazy magic. This is almost fun, chasing those around. Okay, so now the bits of information, I had so much fun erasing that. The bits of information that we're looking at for this problem is that it's a left tail, and I believe it said significance alpha level was 0.10, 0.10. So that means our critical value has to be this guy right here. That means that z critical value is a negative 1.282. If I can get to it, where'd it go? Here it is. Okay, next. Compute the value of the test statistic. Round your answer to at least 2 decimal places. Okay, so our test statistic is going to be in our chart, our formula sheet. And it looks very similar to before. There it is. You've seen that one before, actually. And that's finding z-scores. And I think what I'll do is I will write that. Let's write it right here. It's going to be z equals sample mean minus the mean from my null. So I put a little sub-zero there for that. My null statement, okay? And then down below it is sigma divided by the square root of the sample size. So now when I put in some of this information here, my sample mean is 19.2. My population mean from the null hypothesis was 20.2. And I need to divide this by standard deviation, population standard deviation 4, divided by the square root of sample size, which was 107. So in the numerator, I'm going to get what, a -1 when I subtract that. The denominator, I'm going to get, and I would not do much rounding at all in this. I would put as much value as you possibly can on your computer screen. Let that go as far out as possible. So we have as accurate as we can be, and then round in the very end. We get a -2.58602, and then let's now go ahead and round to 2 decimal places for the answer. So I'm going to say z is approximately equal to -2. Let's round it to the nearest 2 places, so 59. And there's that answer. Okay, so -2.59. So what is going on here? So I want to draw you a little picture. As you know, I love pictures. And I want to kind of try to explain what is happening with this hypothesis test. So basically what's going on here is we've got our standard normal, where we have our mean now. These are z values. We have our mean at 0. And we know when we translate our z values back to the raw scores, basically we're talking about our mean right here which was, we said that, what was the null hypothesis? If I go back to that, it said that so what's assumed is that the mean is equal to 20.2. There was a scientist that said, I think maybe the mean is less than 20.2. So we went out and we did some sampling. We got our sample mean, and then we take that sample mean and turn it into a z-score. Now, that sample mean could show up anywhere on this distribution. We're not expecting that sample mean to be exactly the population mean. That would be kind of unusual if you did a sample of 107 people and that was exactly the same mean as the actual population of the whole world, let's say, okay? But we're also expecting it to be, somewhere in the ballpark. In this particular problem, the significance level, or the alpha, was set right there at being 0.10. Now what this means is when I place my test statistic, okay, and by the way, the critical value, remember we used 0.10 to find the critical value? We used 0.10 to find the critical value. It's basically telling us this is our cutoff point. Our critical value here was negative 1.282. So what this is saying is that we go out and sample, right? And even though our sample mean is less than the actual population mean, it's not enough information to go against the assumed thing. Is what we said the mean was what, 20.2? And, because by chance it could be lower. By chance it could be lower. By chance you can get a sample mean way down here. But what we're saying in this problem is that if we get into the probability that's less than 10%, we're saying, okay, by chance I don't buy it. I believe that if our sample mean is below that 0.10 or 10% threshold, I'm going to reject my assumption of the null, and I'm going with my alternate H sub 1. That's what we're saying here. Now, this is the setup for the test here. Now, let's go and take a look. What was the actual test statistic, right? What's the actual number? Remember what we did. We took our sample mean and we turned it into a z-score, and where did it land? It landed even further away from my mean, which makes me very suspicious. And with this standard, because I'm into this, let's call this red. Whoops. Reject zone. If our test statistic lands in that rejection zone, remember, okay, there it is. It's definitely further to the left, negative 2.59. If it lands in that rejection region or zone, we have to reject the null. So let me go back to, what was our initial setup? We said that H sub 0, we said that mu is equal to 20.2. And then we said, okay, the challenger is, we think maybe, what's the alternate hypothesis? Well, maybe mu is less than 20.2. We went out, we did some sampling, we found out that our test statistic from the sample is so far off the mean, it's past my critical point that I got from the probability of 10%. It's less than 10%, it's past my critical value. So what do you do in that case? We reject the initial value, the initial assumption that mu is equal to 20.2. It's not. Okay, so we reject H sub 0. So which is number right here. Okay, so we reject the null at 10% level. So what's your conclusion then? Well, if you can reject the null, then you have a strong conclusion. If you do not reject the null hypothesis, then your conclusion is kind of weak. Because if you don't reject it, that doesn't mean you're accepting it. It just means we don't know. Okay? But once you reject it, that is a stronger statement. And look at, once I reject it, I cross it out, and I go with this statement, which says that there is enough evidence to conclude that the mean time for Facebook visits has decreased. And that's the decrease right there, right? So that's how that goes, right? We do a test, and if our test statistic from our population or from our sample mean is so far away from the mean, we say this is looking a little fishy. I'm going to reject that. Okay, and how do we know whether to reject or not? Well, once again, if your test statistic lands in this region, then you're going to do not reject. Do not reject. However, if your test statistic from your information, from your sample, lands into this region, then we are going to reject. Okay, and that's how that works. All right. Let's take a look at another one. Now, the difference between this problem, the conclusion, so the test is testing the same scenario. It's just we're using a different method called a p-value method with the table. Okay, so we can use, we're gonna need to use a table. You could also use a calculator, by the way. But the table's pretty easy with this problem. It's accurate enough. But anyhow, let's take a look. All right, so are you smarter than a second grader? A random sample of 62 second graders in a certain school district are given a standardized mathematics skill test. The sample mean scored. Okay, so right off the bat, this time they're given us sample information. So let's write that down. That would be the sample size is 62. They're giving us that this sample mean X bar is 57. Assume the standard deviation scores. Now they're giving us the notation. This is population now. So this population standard deviation is known at 14. The nationwide average score. So now we're talking about population from this point. The nationwide score, mu, is 59. The school superintendent wants to know whether the second graders in her school district have weakened. And to me, weaken means less, right? And we don't want them to weaken their math scores. We want those math scores to go up. But weaken their math scores, skills, let's see, school district have weakened math skills, then seems like that doesn't read quite right. Anyways, weakened it compared to the national or nationwide average. We're going to use that same alpha this time. Remember, there can be different alphas. You could use any alpha really, but there's some common ones, and that's what we have on our chart. So let's get to the business of figuring out what H sub 0 is. And H sub 0 is going to be our population mean. Remember, H sub 0 will always have an equal sign involved. And so that helps us kind of remember that. Whereas H sub 1 is going to have some kind of inequality, not equal to it, less than, greater than. And we know that because they said weaker, that sounds like a less than, doesn't it? So then our H sub 1, which is our alternate hypothesis, is going to be mu is less than 59. And because it's less than, it is a left-tailed test. Okay, continuing on. They want us to compute the value of the test statistic. Remember that equals X bar minus the population mean, specifically that we got from our null hypothesis. And this is all over standard deviation. And it's a population standard deviation, sigma, which is which helps us, we did get sigma, so we know we're using this formula, divided by the square root of n. And if we put in those values, we get 57 was the sample mean minus 59, which is the population mean, divided by a sigma of 14 and a sample size square root of 62. We subtract and we get a negative 2 in the numerator, down denominator 1.778, 1.778001. We do that division problem, we get approximately negative 1.124858, and so on. So it says let's go ahead and round to 2 decimal places in that final answer. Z is approximately equal to negative 1.12. That is our test statistic. So remember, something to remember is that this information came from our sample mean. So this is representing our sample. It's good to remember. This p-value method, once again, does a similar thing, but it does it in a different way, and it can be a little bit confusing, bouncing back and forth. So you really have to try to lock in the difference between p method and critical value method. So let's get this p-value first of all. And the way you get the p-value is you take your z-score. Oops, there it goes, switching back on me. Let's see. You take your z-score and you convert that into area. So, and it's area to the left of z, and we're doing a left-hand tail. That helps us understand that. But here's the thing. The name p-value comes from probability. And probability, remember probability, when we're talking about these, the standard normal curve, probability or proportion is just, the area under the curve. So a p-value is actually the area, okay? So I want you to try to make a good distinction between z-scores, right? Z-scores, which z-scores are basically, the numbering system, but the area, p-values are going to be the area. Okay, so try to have a distinction between those two things as we go ahead and try to build this model of what we're doing. Some of this is very similar to, well, a lot of it's very similar to critical values, and that's probably why it gets confused. So now we're going to do this as z-values, okay? Just to kind of get, I can't help it, it has to be z-values because that's what we're working with here. But with the p-value method, we're more looking at the area rather than specifying on the z-score. Let me go back here. Notice we're focusing in on the z-values to figure out if we're going to reject. With the p-value method, we're going to be focusing up on the area up here to figure out if we're going to reject. So that, I think, in my mind, that is like the big difference. It told us that we're going to use a critical, not critical. They told us they're going to use a significance level of 0.10. So once again, alpha 0.10. Which means what? Which means if we're doing the critical value method, it would be okay if we get into this critical region, we have to reject, right? But this particular problem, we're looking at p-values, which is area. So basically, if our area is smaller than that area, we have to reject. If the area is bigger than the area, we do not reject. Okay, so how do we do this? We've got to figure out what the p-value is. And the p-value is just going to be the area under the curve to the left of negative 1.12. So we can just look that up on our table or calculator. And I think I included that negative 12 is going to put us at that place right there. So let me draw that down. What did I say? Negative 1. So negative 1.1 is right there. Negative 1.12. That's the z value, and what does that give us? It gives us an area of 0.1314. So right away, you should be noticing something. We're saying if our sample mean is somewhere in here, once again, that could be just due to chance, right? That could be just due to chance, and I don't want you to be thinking about this like I'm talking about z-scores. I'm talking about area, so it gets a little bit sloppy. But if the area is somewhere in this region over here to the left, then that's bigger than this little red tail. But if my p-value, which is the area, is smaller than this tail, then I'm going to have to reject, because it's all about how far away from the mean it is. And once again, this is going to be our dividing value that tells us if we're going to reject or not. I'm going to try to make that really clear right there. And it's not about the critical z value now. It's about the area. And we just found out that the p-value, which is the area, is approximately 13%. Well, that's definitely bigger than 10%. So if I was going to draw the p-value in here, a lot of times they don't do this. But if I was to draw the p-value, this p-value is 0.13 or 0.1314. Notice it is in my fail to reject area. It's not far enough over. Right? Notice it's in this area. It's only up to there, which means the area to the left of that is bigger than the red area. So I'm not going to reject. How would I know if I had to reject? Well, if my p-value got smaller than this, now remember we're talking about area. So if your p-value is smaller than 10% or 0.10, then you would have to reject. Once again, go back to the green. Whoops, that's the wrong green. This is do not reject. So we're in the do not reject zone. So it says determine whether to reject. We do not want to reject. Do not reject the null. Okay. And if you do not reject the null, then we can't go with the alternate, and we have a very weak statement. And the weak statement is there is not enough evidence to conclude that second graders in the superintendent's school district have weaker math skills. We can't conclude that. We cannot conclude that because our sample data didn't get us into this rejecting area of less than 10%. All right, I hope this helped out, and I tried to do as many little pictures as I possibly could. Hope everybody is safe and COVID-free, and take care. Bye.